Hi everyone, my name is Kate Johnson and I will be starting us off with the AFRL Design Competition Final Design Review for the Utah State University team. So, if you were able to see our CDR, our design stayed pretty similar to the bot that you see in this picture, which we presented in the CDR, so I will jump right into our design. So we have the same team members as have been on for the duration of the semesters: Isaac Freusland, Jacob Gates, Mike Graham, myself, Cade Johnson, Quinn Moon, Joseph Pitt, Brandon Ritchie, Joshua Shoup, and Kobe Topalian. So our problem statement was subject matter experts in civilian and military sectors have a need to place cameras or sensors in hard to reach places, often on walls and high surfaces, for security and intelligence. And this is more what our subject matter experts wanted us to focus on, which we will get into here in a second. These cameras or sensors need to be deployed quickly, stay well in place, and be an economical system.
So this is the model of the RC car that we are currently using. The idea of the RC car is to transport the mini climbing bots as seen here. The mini climbing bots are placed on the RC car and the RC car is driven to the wall. We're aware the RC car itself is not anything too special, it's just the model that we are using to demonstrate and test the mini bots designs. Nice RC cars can be used, it would depend on the scenario that the Air Force or the FBI would want to use. Essentially what would happen is the user would man the controls at a safe distance. He would drive the RC car using the camera. The camera is fully functional. The user would be able to drive and see from the camera, drive the RC car a good distance away, wherever is necessary, and then they would switch controls to the mini-bot, and the mini-bot would leave the RC car, the mini-bot could climb a wall, and the RC could return. In this fashion, the RC car serves the purpose to transport the mini-bots in the safest way for the user and without damaging the mini-bots.
So the control system for our bot and climber are based off of this controller, which is compatible with both the RC car and the wall climber, and then this monitor, which is compatible with the cameras on both the car and the wall climber and can toggle between the two of them. So if you want to come around, I can show you this controller gimbals the camera and it can be seen on the monitor.
We had a few specific goals for this iteration based on the performance of the last robot. We wanted the whole bot to be lighter overall, and the wheels needed to spin at a much lower RPM and higher torque to allow for a much more controlled climb. We wanted to implement a worm gear into the drivetrain to keep the wheels from backdriving. This would keep the robot from rolling back down a surface once the motors were no longer powered. We wanted to be able to plug in any off-the-shelf RC transmitter and receiver. We also wanted to have a better weight distribution and look into having modular parts. So having modular parts like the motors, tail, and wheels would allow us to experiment with different configurations and better optimize for performance in different situations. So I started with the motor and gearbox when beginning this design because the motors are going to have the largest impact on the overall performance of the bot. Every other component was chosen based on the input and output parameters of these motors. We looked at and compared around 25 different motor models, and we ended up choosing these N20 motors because of their low weight, high torque to weight ratio, and they had sufficient torque for climbing, and because they have a built-in gearbox with a worm gear drive.
This is the subsystem overview for the gimbal camera system. In our second iteration, we still have an enclosed gimbal system, but this time with an improved camera. With higher video quality and the ability to record audio, this camera is lightweight and gets the job done for sensing the environment the mini-bot may be placed in.